Right. Okay, everyone. Today we're going to talk about agents, a very timely topic. The outline of the lecture today is that we're going to first, what we're going to do is we're going to go back a little bit. We're going to talk about AI agents in the pre-LLM world. And this has to do with this kind of concept of what's called the rational agent. Russell and Norvig were the ones who wrote this kind of uh, classic, they wrote this classic AI textbook, AI, A Modern Approach. And when I taught AI, I was using an earlier version of Russell and Norvig, but the last version they had was 2022. But they have they have what's regarded as, it's a highly regarded treatment of agents in that book. So I would like to review that. I have a tendency to say that it feels like sometimes that the whole LLM crowd just fell out of the coconut tree because they kind of seem like it seems like everything starts in 2022, but it doesn't. Um, okay, or 2017, if you talk about attention is all you need. But we're going to go over that because I think it might be useful, and in the conclusions we'll wrap it back into that to kind of make some statements. And then we're going to go into maybe what's more interesting, more timely, is as agents in the LLM world, and we're going to talk about some definitions, some infrastructure. And then the three systems we're going to want to talk about is one is called Baby AGI, um, and then we're going to have a kind of a knockoff of that, which is even simpler, Turtle AGI. Then we're going to talk about Claude Code, which I'm sure many of you have heard of. And then we're going to talk about OpenClaw, the lobster. And then the conclusions. So let's get into it then. Okay, so the classic way that you look at agents, which is, I think it continues to today, is that agents are in this sense, think, act cycle. So the idea then is that what we have is we have the agent, and that we have we have the environment. So the most fundamental is that we have an agent and we have an environment in which the agent is acting. And the environment at a time step will form a percept, then will basically impinge upon the sensors of the agent. The agent will then decide from the sensors which actuators it will activate to produce an action in the environment. So this is all very abstract, all very basic. So that goes on. So I think that it's instructive to talk about some example agents that we're going to just kind of entertain here. So, uh, so some of these are kind of more on the weak AI. So there used to be a distinction in AI between weak AI and strong AI. Okay, weak AI is kind of more of an engineering kind of approach where it's kind of like, can we solve tasks that seem to require that previously had been considered to necessary to have intelligence to solve. So things like recognizing faces. So if we have like a big database of different people's faces, and what we want to do is take a picture and then say, is that John Doe or is that Sam Smith or whatever it might be. So that's basically that's what this agent is doing. It's very, very simple. You just flash it an image and it tells you who it is. Um, then we have another one, which I think is kind of instructive, is this, I'm not sure what I think you guys call it memory in Swedish, but this card player where you basically have a set of cards on a table, right? And then like basically some of them are the same. So this might be like the seven of, this a seven, and this is a seven. And then what happens is that they're all like face down. You flip one, and then you have to just kind of randomly flip another. So let's say on the first trial, I flipped this one, and then I flipped this one. So this and this showed. Then I turn those over again, and then I basically flip four, and I'm sorry, I flip four, and I pick this one. But if I have a memory, if I'm kind of keeping track of it, I say, oh, if I match them, then I can get rid of the cards on the table. So then on the third iteration, I would pick this card and this card because I know they match. Okay. So that's kind of it's a step up from this because this actually does require some type of memory, if you think about it. You can't do this well, you can do it, but it would just be very inefficient where you would just kind of, well, uh, the, to play an optimal game of concentration or this card game, you need a memory if you want to play it optimally. And then we'll talk about what optimal means in a second. Then we have chess. Of course, we all know what chess is. This adversarial game back and forth. And then let's just hop up to something a bit more extended, and that is like a self-driving car. So a car that is that not in this case here, then we're talking about a very much a rich set of percepts and actions, right, for the self-driving car. And then the final one we want to talk about is a chatbot aimed to pass the Turing test. So a chatbot is supposed to kind of appear, or basically a chatbot that is indistinguishable from a human. Okay, so if it passes that, that's an objective criteria. I mean, if we give it 50 people and they half the time we're chatting with a human, half the time they're chatting with a machine, and there's no like they can't discern if it's a machine or if they're human they're talking to, then we've passed the Turing test if we can do that repeat in a repeatable fashion. Okay, so those are our example agents that we'll kind of keep in mind. Now, this is kind of important to kind of consider here. This is kind of a nice bit of formalism on top of this. So if we think about it through, and this is through time, we have we have what's called the agent function. Okay, this is what the agent actually does when there is a sequence of percepts. So this is like the whole history of the percepts that it's presented with, the whole sequence of actions that it's earlier um, performed, and its own internal state. Okay, and these are notice that all of these are these three structures are finite because there's a finite number of percepts that's come in, there's a finite number of actions, and the actual state of the agent is realized on a finite machine, so it's going to be a finite state. All right, okay, so the agent's behavior can be externally described by an agent function, which will take the SPA, it'll take these as arguments, and it will determine what is the action at the next time step. Okay, and if you were to actually try to build this as a table for anything but the most trivial agents, this becomes a table that would be of form beyond countably infinite. Okay, so there's no way you can't even write the table down that would capture this. Okay, so an agent program, however, is a finite implementation of the agent function. It is not a table. It is a finite implementation running on an agent architecture. But the key thing here is that there are, arguably a countably infinite number of different like SPAs. But if I pick any particular and I basically have a function that's in implementation, then that determines something that's beyond countably infinite in terms of its behavior. So it's a very strong this even though it's a finite program, it can be put into any certain and any into any environment and it's going to do something, or the action could also be do nothing. But the point is that there are beyond an infinite number of different situations you can put the agent into. But if you have implemented an agent function, it will always do something in any one of those environments, okay, or histories. Okay, so I hope that that's kind of a little bit abstract, but it's important to, it's that's this is kind of the setting. Now, when we talk about environments, then what we're doing is we're going to wind up classifying the environments in which the agent's going to run. So one of the most important questions is it fully observable or only partially observable? So chess, except for the en passant rule, is fully observable. You can look at this, if you know who's next, who's going to go next, black or white, you can look at the table, you can look at the chessboard and you can basically determine, okay, I can fully observe the environment. Okay. That's not true, however, in something like self-driving car, right? Because you don't know, there could be an infinite number of things that are beyond. Like you're basically having a camera, which is a 2D projection of a three-dimensional world. And when there's something that's occluding something, anything in principle could be behind that occlusion. So you don't have a fully observable world. Okay. The next thing then is that we talk about the actions. Are they deterministic or stochastic? So in chess, it's deterministic because you just pick what's the next piece you're going to put down. Okay, that's easy. And it's not like you're going to miss on that. Self-driving car, though, is stochastic because you might turn the wheel and you're not necessarily going to get exactly what you want. It might be a little bit off. So it's going to be a stochastic result of the action. Then we have the notion of episodic versus sequential. So is the experiments divided into atomic episodes? Um, so in the case of face recognition, it's atomic because yeah, you trial the agent by just flashing another face up there. But when you talk about any of these games, then it's going to wind up being sequential because experience winds up being well, the experiment, like in the case of the concentration, you have to take into account your kind of prior experience to play a rational or to play an optimal game. Um, now, then there's a question of is the environment static or dynamic as you're deliberating? And in self-driving cars, it's definitely dynamic. In the case of chess, it's static, unless there's a timer, which means it's semi-dynamic. So if you have a timer, if you have a clock, a chess clock you're gonna get scored, uh, you're gonna get scored down if you take too long, then it actually winds up being a semi-dynamic environment. Discrete versus continuous. Chess is discrete, right? Self-driving is continuous. Okay, it just has to do with, and this can apply over the state, the time, the percepts, or the actions, etc. Um, and then finally, we can talk a little bit about is it single agent or multi-agent? And we're not going to say much more about that, but that's these are the kind of these are the dimensions that environments are kind of judged by or they're partitioned by in the classic work on agents. Right. Okay. Now, here's where this is where the classic. This is where we're going to see later on the LLMs are going to depart from this. But what the classic models do is they make what's called the ideal rational agent assumption. Okay. So basically, what we want to do then is we want to have a performance measure. We want to say what's good and what's bad, and then we want to pick the action that maximizes the performance measure based on the available evidence. Okay. So how and when do we evaluate this performance measure? How is objectively and consistently using the performance measure. That's how we just evaluate success. So this is kind of important because sometimes the performance measure, I mean, humans are famous for kind of altering their performance measure. So like the sour grapes thing is that, well, all those Nobel, I don't, maybe I used to want to get a Nobel Prize, and then later on I think, oh, all those kind of pretentious kind of judges and all that. I don't really want to have anything to do with those people. So I affect my own performance measure so that maybe it's just for my own happiness or something. So it's this kind of loving one's lot kind of thing, or the grass. And then the opposite would be the grass is greener. You get something and then you say, well, this isn't really worth it, and then you search out other things. So performance measures are in humans are very slippery. Um, and then a key thing here, though, about the performance measure is you want to at least put it on the environment rather than on the actions. So it's kind of like if I have a performance measure for like salespeople, and I say, okay, I'll give you some kind of like little bonus or whatever for every person you talk to, every call you make. Okay, that might not work out well because then they might say, oh, okay, well, and they make calls to people who aren't going to like pick up the phone or something, so they can just kind of rack up the reward. Um, but if you put it on something that in the environment, like that they don't control, like the actual customer making a decision to buy something, that's a better performance measure. Okay, and then there's always the question of when are you going to actually do the evaluation, and this has a lot to do with this kind of rates of discounting the future. So yeah, so the execution joke was this joke about like a guy's about to get executed, and the guard hands him. He says, here's your last cigarette," and then the person being executed that's going to be executed says, "No, no, thanks. I don't want to smoke because I'm trying to quit." Okay. So that's the execution joke because it shows the kind of a little this mismatch, and I mean he only has 10 minutes to live, so it's kind of it's a little bit topsy turvy. Another thing also is that this it tends to be they say that like people who are in more stable environments can have a longer discounting of the future parameter. So like gangland, I mean, someone might say, "Oh, it's so irrational for these gangland people to kind of grab at resources and steal and do all that other stuff." But if you look at I'm not going to excuse it, but if you look at the discounting of like the chances that they're not going to survive, you put someone in a situation where they have the future is there's no worth or there's no very little value in the future, then you're going to get a different discounting factor. Okay. Another thing also was rationality and omniscience. You can't judge an agent for things they couldn't possibly have known. So like you can't judge a trading agent based on the closing prices for all stocks at the end of the day because nobody knows that. You'd have to be omniscient to know that. So this is just another thing you have to kind of keep in mind. Also, the thing is that what's interesting is that what falls out of this is the is information gathering actions. Look, they can be fully explained by setting up this this kind of logic or this kind of regime. So you can kind of, if you think about it, you can actually come up with an explanation for information, like looking before you cross the road. Okay, finally, let's get to this. So let's get to this. There's the notion of an agent architecture. So what is the agent program going to actually run on top of? What is the actual physical machine that it's going to wind up being instantiated within? Okay, and we're going to see that we have several different uh, several different choices here. So again, remember, the program is this thing that determines, given the state of the agent, the percept sequence and the prior action sequence, determines what the next action would be. So you're going to run you're going to run you're going to run the program that implements this on top of the agent architecture, and that will actually give you the agent that you can then place into the environment. Okay, so we have the simple reflex agent, which is stateless. Okay, there's no state. Okay, so it's just basically working on stimulus response. And this would work for things like the face recognition problem, because we don't need to have any model of the world, but we better have full observability. We better be able to see the full world. Okay. Um, right. So multi-layer perceptrons, if you kind of code things up, those actually are a simple case of this as well. Because if you think about it, like it's just like the signals come in, that's the what comes onto the sensors. It washes through the multi-layer perceptron, and then we might have like at the end, we might have a softmax that decides what action do we take next, and then it takes the action. But there's no storing of any kind of state. Then it's done and it's ready for the next observation, the next problem. All right. Well, one step up from that is something that has a internal state that's represented in a memory. Okay. The so what we see here is the sensors come in, and basically what they do is they wind up we kind of do a quick analysis of what the world is, and then that feeds a state, some state object or state something we're holding over the case. This is agent state then. So that we're holding over that will persist inside of our memory. Okay. And then there might be knowledge about, well, how does the world evolve? What do my actions do, etc. And we might have some kind of something that will basically then say, okay, what action should I take now? All right. And then it will actually do the action. So notice here that something like implementing the concentration player now, we could easily do that within this architecture, but we couldn't do it in the earlier architecture. So we've added something to the architecture, principally the state. Okay. Now this is where gets kind of interesting. And this has to do with goal-based agents. So these also have a state, but what they also have is they also have a capacity to explore basically alternative worlds or alternative states within the actual agent architecture. So basically it works like this. So the agent needs to know what uh, all right, the agent has a goal, and then the goals are usually desires or intentions or something. And then it plays with hypothetical. It has a record of the state here, but then what it does is it kind of says, well, I can do these actions. That would change the state in this way. I could do this action. That would change the state in another way. And what it does is it winds up generating potentially a tree of different possible states that its actions could reach. Okay. And then what it does is it searches out those trees. So it does searching or planning, right? Um, uh, and then basically what it winds up coming up with then is it comes up with a plan to take itself to the most desirable state in this in all in all the hypothetical states under this tree. It's going to come up with a sequence of actions that it's planning, and then it'll execute the first action. Then it'll see how that's going in the environment. Maybe it can just continue to just evaluate the same plan, or maybe it needs to replan as as it sees if things are working or not working. So this is kind of like chess, right? So well, the thing is that you look at your position in chess, and then you start playing with the hypothetical. You build a game tree where okay, if I do this, and then he could do that, et cetera, and then you chain it out deep, and then you basically say, okay, I know, well, if I do this one, I might be able to reach this state. So I'm gonna take this. I'm gonna take this option. So what comes out of all that is one single action. Move my pawn up two spaces in the queen file. Um, and then of course then the environment was going to change because then the other ones are going to play the same kind of game of trying to determine what next action to take, and then you're going to go accordingly. So you're going to do this replanning. Okay, so you could not do that with just the prior one. So if you try to play chess with something like this, it would be very difficult. Although people have kind of tried, there's some interesting results there actually research wise. Right. Okay. So this is the game tree search or planning in the more general case. This is kind of what these goal-based agents do. Okay. Now we get into we're going to move up even more complicated. What if we don't really have a single goal in the world? We have kind of a mix. We have a mix of different. We score a state based on more than just one factor. Okay, it's not just getting it's like some trade-off that you want that you're going to score the state in. So sure, you want to have some money, but you also want to have health. So if you can't, you don't want to go, you don't want to completely kind of ruin yourself pursuing money. But then again, there's like a trade-off, right? So doing some actions to kind of get money make a lot of sense. If you don't do it, then you're going to suffer. The state you reach is going to wind up being a state in which you suffer. So the way this tends to work is that we have so if we have multiple goals, how do we weigh goals and probability to attain the highest utility function or performance measure? And basically, the way this tends to work is this maximize expected utility. Okay, so and that can handle conflicting goals. So the problem with maximize expected utility is that it's not as discrete, so you wind up having to step away from like it's harder to do with first order logic or logical representations. So a lot of times what you'll do is you'll move something to something that's propositional, like a Bayesian network plus a decision component. Okay, so these are all kind of in the classic AI world. And then finally we get to learning agents. And these are kind of a little bit more abstract here, but the idea then behind it is that basically we have the performance standard coming in. We have a critique, which will look at us and kind of see how we're doing. But we have the sensors, the performance element, and the actuators. And then what we do is we wind up into the learning element. We have this critique. We have feedback from the environment, and then the learning element then can make changes or install fresh knowledge into the performance element so that it improves in this way. Another interesting aspect is to generate new problems to do explorations. That winds up becoming this exploration side of the exploration exploitation trade-off. So some of the things just to keep in mind with this is that the agent program, so performance needs to be communicated to the agent. So you need to have something that's going to kind of give feedback here, give kind of a positive or a negative signal, not just kind of what's going. I mean, usually what it is, the way it gets incorporated into an environment is if you wind up in a bad state in the environment, you get a pain, a big negative comes in, or a big positive in the case of a pleasurable state that you're in the body. The environment is what's feeding these to the agent. So this is kind of in the biological world. This is kind of very much inbuilt into the actual agent program, and that comes down to this issue of the agent program. The agent program itself can happen at design time or online, so as things are happening. And there's this kind of famous example of a dung beetle. So a dung beetle is a little beetle that will go out and grab a little piece of feces or shit, and then it will plug up its burrow with that piece of excrement. And the thing is, if you see a dung beetle going along with a piece of vise on its back, and you flick that vise off of the dung beetle's back, then the dung beetle will actually go in and it will go into the burrow, and then as if there was a piece of dung on its back, it will mimic the whole kind of routine of plugging up the hole with just with nothing because you flick the piece of dung off of its back. That's showing that it's completely instinctual. It's kind of completely kind of baked into the agent. Um, Whereas if you took a person and you did that, the equivalent, they would be like they would have the ability to basically not just be relying on their agent design time. They could take that experience in and change their behavior immediately. And we say that in that sense, they have autonomy. Okay. Now, finally, with learning, there's always this kind of stability plasticity trade-off, and that is that you want to once you get start, and usually what happens is you start out fairly plastic, so that you let the environment change you, and then you slowly kind of cool it so that you wind up going into some kind of stability, so that you're not so that basically what you don't want is you don't want to be always a function of the last experience you had. But that might be better to have that tendency when you're younger, and this is all happening on top of some kind of fixed kind of instinct or something. Okay. So this is the again this is the classic way of looking at agents. And again, remember that the key thing is the idea of prizing the rational agent relative to a performance measure. Okay, so that's how things get set up. Okay, but that's not the world that we live in. Okay, so so is this really it when it comes to agents? Is this really it? Okay, so well, let's think about it for a second. So the question is basically, can agents really be modeled as an optimization problem? Can we really kind of see it that way? For weak AI, yes, mostly. So I mean, for things like even like playing Go and playing chess, playing Go, even self-driving, right? Yeah, you can think maybe you can model it as an optimization problem so that you're maximizing. It's in the case of self-driving, it's over a mix of goals, so it's utility based. But yeah, you can kind of see it as a you can see it as something that maybe can be achieved with this rational agent assumption. Okay, but when we get to stuff like AGI, strong AI, then the answer is probably not. There's more to it than just having some kind of optimization function that we are maximizing. And then for ASI, artificial superintelligence, that probably not as well. Okay, so that kind of follows. Um, so let's just kind of think a little bit. What is it though then that is maybe potentially uh, uh, to get AGI or to kind of think more generally about agents, what is it maybe that's missing? So let's just look a little bit at the foray into human intelligence. Okay, so there's so let's just kind of like go through this. So there's two basic theories of the evolution of language because language is the ingredient. Now we can argue about whales and we can argue about like some birds and even chimps. We can argue about those things. But there is something special with language that humans have, right? That it's we don't see. So there's always this thing of like saying that, well, a bird can t say to another bird that a predator is near, but a bird cannot say to another bird that he has mixed feelings about his parents' approach to sternness and education and how they raised him up. Okay, so a statement like that, or the bird does not express some kind of political feeling about the current ruling class and how how they behave. Um, so the point is that language somehow there was this kind of there's a quantum leap in terms of what is being expressed between communication in animals and communication in humans. So that is very much at the root of probably something going on here. Now, just to keep, and I'm not going to go too much into this, but there are two basic competing theories of the evolution of language. There's the one that says it was gradual, so it happened as a gradual kind of progression. So we went to Australopithecus, Homo erectus, Neanderthals, Eve, and then the sapiens. And there's another theory that says it was a big bang, that something happened in the architecture of the brain that allowed for this kind of language organ to just pop into existence. Okay. Now there's some supporting evidence about that because of art and this kind of abstraction. Art appears late. But then there's a lot of people who are saying, no, it was more gradual because the question is if you go back and listen to how Homo erectus were speaking to one another, when did they start talking about things that didn't, that were more abstract and kind of removed from the direct um, uh, one-to-one kind of system of animal signaling or communication. So the animals tend to have what are called one-to-one theories of reference. So basically, an animal talks about something that is directly or has been in their environment. So they're talking about things that are concrete, predators, food sources, etc. Things that are like, well, they signal maybe like mating or something, or they have these are concrete things. So they had this kind of pre-linguistic intelligence, but then for humans, when we listen to a conversation between two humans, it's almost always that they're not talking about things that are in the environment. They're talking about meta concepts or prior utterances of humans or something more abstract about prior humans. So the whole kind of theory of reference that is kind of grounded in the logics completely goes out the window. So we don't really have. There have been attempts to try to formalize it, but it's very, very hard because if I say these kind of abstract, I mean, we're not talking mostly about the. I mean, we are indirectly talking about the real world, but mostly we're at this huge abstraction level up from the real world. So, what are human beings really talking about? We don't know. But anyways, at one point or another, humans started talking to one another. Okay, so they either it was a gradual thing or it was a big bang that you just had like this Eve hypothesis that it was something coming down from in the mitochondrial DNA of Eve, and that gave well, she would when her descendants when they mated with a normal like human grade at that point, since it's coming from the mitochondrial DNA somehow, then it gets passed down. So Eve was passing it down to everybody, and then this language or this kind of art, this kind of like true language expressivity, kind of passed over all of her descendants. That's one of the theories about the Big Bang is that we had this Eve. That did that. But anyways, we have humans in there. So we go back maybe, I mean, I'm sure if we go back like 40,000 years, well, we don't know, but we go back 40,000 years and there's a system of language. I mean, people are talking to one another. There's like they're saying things to one another, and they're saying things that are pretty abstract, most likely, but not so abstract because the problem is that everything gets passed down by an oral tradition, right? So what happens, right? So writing happens, and when writing happens, what that basically is, and here we are. There's a pre-cuneiform, uh, basically 32 to 3,000, 3,200 to 3,000 years before Christ, so about 4,200 years ago or something. They come up with a system of phonetics to how you articulate like whatever that spoken language was to some kind of physical representation of it. That became kind of stamped into things, and they were etching on tablets or stones. Um, and one thing to keep in mind here, which is kind of a funny thing in a way, why did they even start doing this? Why did they even start putting things on stones? So this is the original Enterprise app because the first thing was it was about ownership and kind of tallies of bill of sales. So it was invoicing. The reason why Cuneiform started in the very beginning was invoicing. Okay, that there our very first examples of cuneiform are invoicing. Just okay, making or making a record of sale or making keeping track of debts and that kind of thing. But once they did this thing where they were get the phonetics to the physical representation, once that kind of clicked in, then you have things like the Epic of Gilgamesh. So the Epic of Gilgamesh from Sumer, that's the first like that's the first work of literature. Okay, but then it explodes, and so then we get to this situation where then we start having culture through tablets, through papyrus, through paper, and then onto files, right? So what we've done here then is that we have, and then what happens is that the next generation can have these concepts because they're written down that then pass to the next generation, and you start building up a repertoire, a cultural repertoire of very extended concepts that become the basis of our intelligence and so think of it this way. I mean, so they have these examples where these unfortunate children are raised by like a wolf or something. So they miss out. They never get anything. They never get anything imparted to them. So the question is, to what extent, like you might consider yourself intelligent, And the question is that all those concepts in your head, those are like, like the concept of like receivership, like of a corporate corporations, receivership, all this other stuff. All those things were passed down to you. You didn't come up with those. Those were given to you. They were passed into you via culture. Okay. And you can't have that without something being written down. Okay. So this is to say, then all right. So when we look at culture, all the culture that's been gathered through tablets, papyrus, paper, and then finally put into computer files, well, do we have a way to carry that onto our agent? All that written information. And the answer is, of course, we compress it into an LLM. So yes. So now we can bring this fresh ingredients. It's very fundamental. So it's not an optimization problem. Well, building the LLM can be framed as an optimization problem, but now we have this kind of baggage that we're going to be carrying into the agent. That's going to be carried in through the LLM. Okay, so we're going to take a break here because I want to make sure I record. So let's get back at 10 after. Let's aim for 10 after. It might be a little longer depending on how long this takes. But then, because based on that whole thing, we have two things here. We have the rational agent, the agent architectures, kind of what's going on with those. And we have the idea now that the written record of humanity all the way up to now is being compressed into an LLM, and that's going to be coming along for the ride. So we'll return with that. So now we're into the agents in the LLM world. We've built up to that. So, okay. Right. I'm going to exit the thing just to kind of get the recording here. So I'll see you guys at 11:10. All right. Yeah. So, now getting back to it. Yeah. So we have access to human culture, everything written basically via the LLM compression. So I think the people, kind of cranky people in my past said that, Michael, not everything, you can't learn everything from a book. And actually, I object a little bit because almost everything has been written about in a book, right? Now, of course, you can't learn to ride a bike in a book, but you can certainly, there's books and it's in the LLM for all like the steps that to take to learn to ride a bike. I mean, in minutia. So most things are written. I mean, humans have been writing a lot, so it's there's a lot there that gets sucked into the LLM compression. So LMs want to become a proxy for human culture or intelligence. So right. Okay. So agents in the LLM world. All right. So agents, agentic AI. So it's basically, let's say agentic AI is designed to behave like a digital employee, okay, or partner. They can reason, plan, and execute complex multi-step workflows with minimal human oversight. Okay, that's kind of a generic, definition of what an agent is or what agentic AI is. Of course, currently there's a frenzy. It's an absolute frenzy in the marketing of this. So you have agentic AI, agents, MCP, agent workflows, multi-agent systems, orchestration. You'll see a lot of these, and there's many more. There's a lot of these keywords that are coming up. So a lot of tech companies are really kind of rushing into this. It is a gold mine of sorts. But one thing that we just want to like kind of keep in mind here is agent washing. So there's a lot of people who just kind of slap the name agent on when it's not really an agent that they're actually offering. They're offering a chatbot. So a chatbot. So what's the difference between a chatbot and an agent? Okay, a chatbot accepts a single prompt with perhaps a context representation. Okay, so there's like the prompt, and there may be like the prior like conversation or something. Something's getting also put into the context, and then it generates a direct response and passively waits for the next prompt from the human. Okay, that's what a chatbot is doing. We kind of know like classic ChatGPT is doing that. Now, a full LLM agent accepts kind of like a high level goal and it plans, executes, and reflects. As so it plans, what's it going to do? It starts executing actions. It starts getting feedback from those actions, and it reflects upon those, taking actions on tools in an active loop. So it's active. This is a very active thing. Now, not all things that will qualify to be an LLM agent do all of this. So simpler variants may do less than a full LLM. So there is actually a continuum as you pull back some of these things, as you pare them away. Ultimately, you'll wind up back with a chatbot. But the full agent is kind of doing all this stuff. So we kind of just we just want to keep in mind that an agent is not a chatbot. Okay, so let's think about the LLM. Let's just kind of think very fundamentally here from the foundations here. So LLMs are what I would call frozen oracles. So they've compressed all of human written understanding, and you can basically send them prompts, and then you get back responses. Okay, so it's just frozen though. You just push it in, and you get something back out. All right. Now in the language here, we're going to call the agent program, whatever, we'll call that the harness. Okay, this has become a very popular term to describe that. We have the prompt with the response, and we have the model. Okay, so there's the model. So these oracle responses, if you think about it, they can be true, false. So you can use the LLM as a judge and say, okay, describe a situation. Is this good or is this adequate? Have we reached the goal? So you're using it as kind of a binary tester on something, and then you'll get back a true or false or an unknown as the response. So uh, but most of the time, or a lot of times, the response you get back is just the literal material that comes back from the completion, from the LLM just doing the completion, and free form. Or you can also say, "Oh, could you please give me structured JSON?" So sometimes the response can be somewhat structured that's coming back. So you can also get embeddings that come back, but there's kind of a limited number of things that can go here. But if you think about it, how broad is this interface? And the answer is extremely broad because you can put in like God knows what prompt you can put in, and you're going to get a response back out. That's one of the beauties of these things is they will always give you back some kind of response. Okay. So if you contrast that with like normal kind of like remote procedure calls or calls out to things through APIs and stuff, in compute, in writing code, those are much more constrained. I mean, they have very fixed kind of input of how you specify the input or to get something out of something remotely. And the response is always it's usually well structured. It can be even just come like a single scalar or something. Um, and so one of the main issues then, though, in this case, it was very, very flexible. It's very, very broad. Um, so the question is that you'd have to think about it like, well, how would you, if this is your programming, if this is now your programming paradigm, where you can, you have all those things that you get normally with a computer, with a computer program, what you can kind of program it to do. Plus, you have this really fantastic way to ask for these oracle responses coming out of a compression of all of human written data, knowledge, whatever. Um, so then one of the main issues, and this is kind of like one of the main focuses now, is how do you actually engineer that prompt? So this, how is it engineered? How do you actually stack that prompt in the right way to get out the kind of response you want? And but if you just like, and then also another key thing to say is that you might have multiple models that are trained in different ways, have different specialties that are in your repertoire. So this whole thing can wind up calling different types of models. It doesn't have to just call one single model, and that it's calling. So it's a very flexible, open kind of thing. And the question is, what kind of programs can you write if you do this, right? So you have the full Turing completeness of the harness. What kind of programs can you write? Okay, so it's kind of a new general kind of thing. Okay, so typically though, we talk a little bit more specifically about the agent architecture for LLM-based agents. Okay, so what do we have here? What are the important ingredients? We have the trigger. And this is a human. Human supplies the trigger. So they say something kind of like, could you solve world hunger? You ask the thing, or you basically say, oh, I need to send a message to Smith declining his loan application or something like that. You put a trigger in, and then what happens is the harness will basically it has a model, of course, that it can talk. What it's going to basically do is going to go through this RE-ACT, so reason and act cycle. So it might go on for like a whole bunch of reasoning, and it might be like to try to figure out what am I going to do, and that might be many calls to the model, and then finally, once it gets enough kind of bearing, then it might actually start executing actions via these tools here. Okay, so there's like thought, it's going to think a bit, it's going to take actions. Then it's also maybe then going to observe what kind of what the effect of the output was, and then maybe take another thing. But it gets triggered by one initial human statement or prompt, and then it goes through all these things. So let's look at some of these components because we're going to reuse this language. We want to kind of be a little bit disciplined about what we call things. I think there's just kind of sometimes you can't enforce that over like the internet a lot, but there's a lot of people who are a little bit like there's all these kind of synonyms and there's these close matches like memory. People have a lot of when people talk about memory, they sometimes what they mean is actually context. But let's just kind of get these things kind of settled here. Right. Okay. The model, we know, that's the LLM. The memory is most of the time it's the file system. So it's this is like memory in the sense that it's not, it's like it's um, a longer term memory. It's not the memory that's just kind of like, just in the spur of the moment kind of memory. That's the context. That's what you're managing in terms of the context. That's what's actually getting funneled into the model is you engineer this context, you put the right pieces into this context, and then you get something back out. But then the memory is stuff that you're writing down. So you're writing down either into a database, maybe, well, into a file system for the most of the systems are going to file systems. There's a little bit of work going on now going out to databases. It could be vector databases as well. But that's what memory is. It's kind of it's not your short-term memory, it's your longer-term memory. In this case here, it's think of it that way. And then we have the tools, which are the eyes and the hands. Okay, so a lot of times people will call it the eyes and the hands. The eyes are kind of things like maybe do a web search on something, right? So you're going to go off on one of these tools, and you're going to go and you're trying to get some extra information to then feed in. Maybe that extra information then comes in and it feeds onto your file system here, so that you have more in your kind of more in your memory here to kind of pull from. And then the context then gets enriched with that, and then it goes off to the model again. And then importantly, we also have hands. So the hands are the things that are actually going to be doing actions. Like for instance, when I said we're gonna take an action where we're gonna actually send the mail off to Smith to tell him his loan application was rejected. Okay, that will be an action because once you package up the right content and you call this tool to say send it, now it's an action that's happening in the world, and now we don't there'll be consequences. Okay. And the output's a little bit funny because it's like, what is the output? The output, ultimately, in this case, I think the idea here would be that the output would just be kind of, okay, what's the next thing you're going to come back to the human with? Okay. So these are not completely autonomous. There is a turn taking that's still going on inside these agents. Later on, when we look at OpenClaw, we're going to see that that's kind of like this thing can just kind of spin forever. Okay. So it's really kind of, it's got its own kind of autonomy. Um, but yeah, so context engineering, again, this context is really an important piece. This context, again, is the thing that you kind of piece together. And for the next call to the model, that's what gets shoved in. And then you get the response back out of the model. And that gets incorporated and handled as kind of a local variable or whatever, a local state representation in the harness, which might get written out to memory. Okay, so this is kind of like these are the kind of fundamental assumptions, the kind of fundamental terms. So we'll return maybe back to this. Just we'll try to always put things in those terms. Okay, now as far as infrastructure goes, I want to talk a little bit about some infrastructure here. Now we've already tasted this infrastructure a little bit with LangChain. So for Python, yeah, LangChain is we're using LangChain in our recitations. So it started as this kind of Python framework that was started by this Harrison Chase. Okay, so the it has access to LLMs, of course, can make the calls out. It has document loaders, which can support a lot of different formats. It has vector stores, and then it has prompts, prompt templates here. So it's got a whole like library of prompt templates that you can get access to. And then the agents then can you can actually kick off processes via the agents. And then there's some other things this a little more extended, LangGraph and LangSmith, which LangGraph is like a way to like try to put this into some kind of graph language that's a little bit like supposed to track dialogue states. And then LangSmith is something that's a commercial thing that allows you to kind of generate traces through through the whole system, so that maybe you'll wind up well, you can maybe analyze those traces. Okay, so the interesting thing though is that this happened right here. Notice here when we have agents here. So this was LangChain was a little bit was early in the whole infrastructural technology. And then the question is, well, how are you making calls out to agents? There was this kind of like they did a lot of experimentation around that. But then what happened was Anthropic came along, and this is actually the way. I think it's going to be a standard that people are going to conform to because it's pretty good. This is a standard that allows you to set up tools and hands and eyes, tools that can sense, tools that can do, and you can have a way. So this is your agent running. It's running on a host, and then what it does, it's a client. It's a client of these tools that are out there advertised, and the tools have an advertisement. They advertise basically. So you might have like so let's say that what we have here is we have something kind of like an email, like Gmail, right? So this is Gmail or something. So it has an MCP where it can, you can actually read messages or you can send messages, etc. So it advertises that it can do that, and the way it does that is it describes in just textually, it describes what it can take as input and output. What are the actual tools that it supports? So its tools in this case would be something like send email, or it's like there can be multiple tools that will wind up being advertised from this MCP server. Okay, and those all then become part of what the agent knows. It becomes part of the memory of the agent that it has access to so it's on the file system, right? It has a list of all the different things it might have access to, along with what their descriptions are. And it may, based on its like planning, it may decide to use those MCP servers and make remote calls to actually achieve actions or to get uh, results where it's doing a sensing action. Okay. So, the actual adverts have tools, resources, and prompt templates, but I just want to say that the most important one is tools. So this is the one that actually gets used quite a bit. The other ones they can be interesting, important. These are kind of like just like files that you can read, and then prompt templates are kind of like, well, this will tell you which templates this thing can take. But in a lot of cases, you won't even get these. I mean, that will happen is the MCP server will only advertise the tools because that's what really is the useful part. Okay, and so the agents dynamically discover and use these. Later on, when we talk about Claude, you have to sometimes go like a command called /MCP, and then you can well, you do it as a command. You say connect to /MCP will show you which MCPs it has access to, but you can also ask it to say, okay, uh, you give it the kind of instructions to reach an MCP, and that MCP, of course, could be any server running on anywhere in the world. Okay, so might have to authenticate to it, but yeah, but it's a very nice standard. This MCP, very nice. Um, Higher level AI friendly abstraction. It simplifies integration, and there's this notion of dynamic discovery. So it really is definitely an improvement from things like Corba, these old fashioned ones that were terrible. Um, but okay, so that's good. So that's part of our infrastructure now. So in the LangChain thing, this old LangChain image was showing how you can talk to agents, but actually what you're doing here, you're talking to MCP servers. That's how you talk to other agents. Okay, so let's look then. Oh, and this is like from last year, but it's still it's like moving much. I mean, more and more. Almost anybody who has like a SaaS tool now will have an MCP server. It's kind of like if you don't do that, then you're kind of it's bad. Everybody's being pushed in that direction, so everything is becoming MCP-ified. Okay. Of course, don't forget there's also just like if you have a REST API, a lot of times the coding agents can access REST API, so that sometimes is good enough. And yeah, right. Okay. So now we talked about some of the infrastructure now, and let's now talk about the very first kind of uh, true autonomous agent, I believe, that got invented. So there were two of them. I tended to go toward Baby AGI in the time. That was what I was interested in. There's another one, AutoGPT. So these were kind of like two of the same kind of similar thing. Baby AGI was a little simpler, so I liked it. And of course, this is like this is from ancient history. It's from March 2023, right? So it's old. That's really old in the LLM world, and that's just like you feel bad even talking about it. It's like Anyways, so the core concept is the loop. Okay. And it was open source, so there was a lot of progress. And the thing to remember, though, is the models back then, again, in ancient history, 2023, the models were not anywhere as good as they are now. Okay, so the underlying models have become significantly better. So this was kind of the baby AGI did some impressive things, but it was doing it over, it was doing it over models that aren't, were, that are there's been major advances in the models in the recent times. Okay, so yeah, so let's nose down into some code here. I'm just going to do a share here. So we'll take a look at kind of how this thing is this thing operates. Actually, maybe before that, what I'll do is I'll just show the output here. So this is actually this something like this will come out if you run this turtle AGI that I supply. So the first thing will be, what is your objective? Okay, so this is the first trigger. My objective is to solve world hunger. Okay, so we'll see how it does it, but this is what actually the log of the thing. So it says, okay, you want to solve world hunger? Okay, support peace building efforts and humanitarian access in conflict zones. Okay, then assess water scarcity and implement immediate solutions, water trucking, well drilling, rainwater harvesting. Okay. Establish and manage emergency food distribution. Okay. So it's really actually is coming up with these kind of set of tasks that we would need to achieve to solve world hunger. Maybe it should say something about US AID because those they cut US aid and they say that 600,000 people are now dead, mostly children, because yeah, U.S. soft power would have been better if they just did. Anyways, world hunger is actually an issue. Okay, anyways, uh, so it basically, but so what it's doing here is it's doing some kind of like takes the overall topic of solving world hunger, and then what it does, it winds up breaking that into a set of subtasks. And then what it does is it says that, okay, fine, here are the subtasks. And then what it does, it's going to order those subtasks. It's going to rank them in terms of like what's the most important. And then it's going to execute that subtask, and that might generate further subtasks. Okay. And then it's going to rank everything on the frontier, right? So these are all on the frontier. It's going to rank them on an agenda. And so it's just going to keep on going down. Now, in the case of Turtle AGI, it'll never come back. It'll just kind of give you that kind of recursive descent on a initial goal. And you could put anything you want in here. You could say get rich. You could say, okay, so what's the objective is to get rich. Okay, and then it'll kind of I mean, it'll give you different subtasks that would be required to get rich. And you could say, what do you want to do? I want to get in shape or whatever. You could put in anything you want, and it's going to wind up giving you like these kind of set of tasks. And the tasks actually make a lot of sense. I mean, it's kind of, again, it's mining this from the LLM. So the LLM is kind of the compressed repository of all the knowledge, and it's getting pulled out by these calls. So let's look at let's just kind of take a look at what the code looks like because it's really simple code. So let's take a look at it. Okay. So let's take a look at this here. Okay. So the very first thing, okay, this is like what it first comes out with. It says, okay, Turtle AGI input. What is the objective? Okay, if I put in solve world hunger, then we're going to get something similar to that log that we saw. But in this case, I can say get rich or whatever it is. Okay, so this right then, this is the actual objective that's going to govern this whole exploration. So if we look right here, we have the objective, and it gives, so what it's going to do here is it's going to basically say, okay, fine, ID equals 1, it's the initial task. And the initial task name is to develop a task list. So this is kind of like the thing that kind of kicks it off. We have the objective, solve world hunger. We have the initial task, which is develop a task list. Then we have an agenda. There's only one thing on the agenda. There's only one task, and that is to develop a task list. Now, this is the loop that never stops unless the agenda runs out. While true, okay, grab the first thing on the agenda. In this case, in the very first part will be develop a task list. Then let's get a raw solution. Now, the raw solution will basically do the following. So if we go here to raw solution, so the raw solution takes as input the the objective, solve world hunger, and the task, develop a task list. Okay, it's taking those two. And then what it winds up doing is it basically does the following prompt, perform the following task based on the following objective. Okay. So the task, why, okay, perform the following, okay, the objective is solve world hunger, and then the task is to develop a task list. And it pushes that into an LLM call. So that's the literal prompt that's going into the LLM, and then based on which model you're using, it's going to then return the raw result of that. Okay, so when the raw result comes back, um, then what it's going to do is it's going to then collect up the task names here. There's only one task. It's the develop a task list. Um, and then what it's going to do, it's going to basically say normalize solution. So this is actually what's okay, normalizing the solution. What that winds up doing, I can probably make this even simpler, but let's look at normalize. Okay, you are given the raw task, the task result. So this is the raw results coming back to create new tasks with the following objective to solve world hunger. The last task that had a raw result is this is the result that just came back, and this was based on this task description, like forming a task list. And then basically it says uh, if there is a task list, then it says, okay, there are incomplete tasks. Based on this result, return a list of tasks to be completed in order to meet the objective. Okay, so now it's doing this kind of ordering. And that's what the normal, and then these new tasks must not overlap with incomplete tasks. Return one task per line. So you say first task, second task. So it's putting some conditions on how it comes back from the LLM. The number of each entry must be followed by a period, etc. So this is just kind of some formatting stuff. And then it pushes that in, and this is where it actually builds out the thing. And let's see here, it's going to basically say the new task, that task name, um, tasks in the task list. Oh, here comes a response here. And then it pulls that out, normalizes it into a list of kind of ranked task names. Okay. Or these are going to be just different task names that don't overlap that come back in the ranking. Then what it's going to do is then it's going to, one sec, then it's going to prioritize the solutions. And when it prioritizes the solutions, that is where it's going to go in. Your task, the prioritizing the following task is the task material. Um, and let's see here. Return, okay, the rank. So this is doing the ranking. But anyways, I mean, you guys can this. I mean, I promise you guys that if you literally run this, it's a little bit, it could maybe be simplified. And maybe I want to simplify it a little bit before recitation, to kind of I want to reduce the complexity as much as possible, but we'll see. I don't, that's the goal behind all turtle efforts is to reduce the complexity as much as possible. Anyways, that'll give you a sense. So the again the log. Now this is where maybe the problem happens. Can you guys see? I'm assuming, yeah. Okay, it looks like it's fine. So this exact log here plopped out of that code. So it's not much code, and this is the actual thing that plopped out. Okay. So that was kind of the initial thing. So people were pretty excited like 2 years ago about baby AGI. But we've come a long ways from then. Okay, one of the main things that's happened now um, is just to kind of bring this up is we're going to talk about Claude right now. But before we talk about Claude, Claude is a coding agent. Okay, so before we talk about Claude, I want to make a statement here, and that is that if you're developing code these days, or that if you're developing systems, you have essentially two options. And the one is to develop code the old-fashioned way, but of course, you're going to use a code assist because it's just you do get speed ups. It's like if I get a bug these days, I mean, I tend to follow this in my own coding. I do the code assist, so the non-agentic way of doing coding. But I use chat because what I'll do is I'll grab use chat to get boilerplate. I'll use chat to suggest refinements or suggest bug fixes. This is like quite common. So why is this thing not working? I'd say, okay, I could think about it, but I'll paste it into like Gemini, Claude, ChatGPT, or Grok. Those are the main ones I use. Paste it in there and see what it says. Because sometimes, especially like with configuration stuff, I mean, it's just God. I mean, it's just okay. It puts you, it speeds you up. It's really nice. It's really nice. But still, I, as the developer, am the bottleneck, but I'm in control. So I'm deciding, I'm literally coming in and I'm putting stuff into the code and saying, okay, now that's part of the code now. But I'm keeping an eye on the whole code. And I get speed ups, but it's still the classic paradigm. It's still the classic way of doing things. And I think this is still going to be around. There are certain things that you need to have, you need to keep in control. I mean, and the developer does need to be the bottleneck because you got to like make sure the thing runs. The nice thing about this also is it doesn't generate that much code. I mean, it's kind of like minimal and kind of easy to maintain. But if then I've done this too, and this is what I think has really caught the excitement of the internet now, or the world, or lots of people who are not even necessarily very technical, but they want to do vibe coding. This is agentic. This is truly agentic. So the idea then is that basically what you do is you instruct the agent to build a work. You might first initialize some code under some directories, and then you instruct the agent to build working systems that take action. So you say, I want to build a dashboard into my database. I want to have something like you basically it's really remarkable what you can say. I want to like stand up a web app that does such and such. I want to stand up a web app that does booking of tennis courts or something. You could just like start with that. Now that's not a good prompt. You'd want to say, if you're, why would somebody might say that if they didn't have any technical background, but somebody with a technical background might say that works under vanilla JavaScript that works under React or that is using a backend PostgreSQL database. They'll add a lot more detail to the actual prompt, the instruction they're giving the system. But then it goes into its agentic loop where it reads and writes code to the file system, and importantly, it tests it, okay, and then confirms the update with the developer. Okay, so now most of the time we'll talk about this in a little more detail in a second here, but how Claude does this. This is more generic. So the other ones are like Codex, and Google has one as well. In its purest form, though, this is the important thing. In the purest form, is you never actually look at the code. You are working with the system at a level beyond actually having to go down into the code, and you only make changes based on your instructions. Now, I have some experience watching over somebody doing this because I work with them, and it's cool. It's really interesting, and it's really amazing how fast the progress is. But man, that code is big. I mean, and it's like 60, it's 60, I think right now what he has it at like 75,000, 60 to 75,000 lines of code and growing. But he's doing it purely on the vibe. There's no going down into that code. It's just, it's not a throwaway, but it's just something at the level of abstraction that you're never going to touch. It's kind of like a compilation. It's like you compile something down, let's say some machine code or something, right? It's like you're never going to go in and tinker with the machine code. You just say, okay, it's ultra high level. Okay. So, but it is really, it's impressive that it is as it kind of works. I don't think it's going to take over. Again, there's going to be a place for this, for code assist. Absolutely. The vibe coding will not take over everything. Like most things have a trade-off. There's always a trade-off with different approaches, but it is definitely a technological result. So it's going to be here, and it's cool. It's kind of fun to work with. But yeah, so that's Claude Code. This is what Claude Code can give you. A lot of times, what you do with something like Claude Code, that you can kind of mix both of these together. You'll kind of like start a project out with Claude Code, just kind of build the boilerplate, build the kind of thing. Tell Claude, hey, could you make this smaller? Could you make this smaller? Try to get it to kind of clean up a little bit. And then you just kind of like, okay, fine, I'll take it from there. And then you take the code out and you start tinkering with the code and you make it so that you could get back to a code assist method. Maybe then you will open it up again to doing some vibe coding if you want to extend it. But a lot of times, yeah, I mean, you might kind of go back and forth. But with the vibe coding, you got to be really careful because you can kind of lose the size of the code becomes so enormous that it becomes very, very awkward to try to bring back into like the classical way of doing things. So Claude Code though. Okay, so Claude Code. And the thing is, in this class, I can't tell you guys to do Claude Codes because it's a commercial thing. But I think it's definitely worth giving a spin if you haven't already, just to kind of get like some sense of it. It runs in a terminal, okay, where you type commands, instructions, and then you answer permission questions. So a lot of times it starts out, it defaults to not being conservative, not kind of going and doing stuff unless you give it permission, like to write to files and which directories can it look into, et cetera, like things like that. Um, so you can kind of protect certain things you don't want to be looking at by denying permission. Anyways, the prompts, like, right, like, write me a tennis court booking application using React and the back end of PostgreSQL. That's a kind of a prompt that will trigger the Claude Code harness to go and start its business and to start writing out files, etc. Okay. So when it's doing this, again, if we go back to, oh, I thought I was going to have it handy here. Why do I not do that? I think I was going to have it handy, so I put it somewhere and I can't find it now. Just one sec. Right here. Yeah. So I'm trying to put it in term. The Claude, they have their own little bit of language about this, but I'm trying to put it back into the terms of this kind of generic agent architecture slide. So we trigger. Okay, Claude never talks about that trigger, but the Claude harness. Okay, they don't call it the harness; they call it Claude. Anyways, uh, when we're doing this, we have the context. So the context is really a really fundamental part of the Claude experience. And you'll see it down at the right-hand corner of the terminal, where it'll show how much of the context have you filled. So the context can be as long as the context window, but you might, like in the beginning, only fill it up by 5, 10%. But as you iterate, as you go further, it's getting more and more stuff packed in there. And a lot of times, one of the most important instructions, these slash commands, is to clear the context or to compact the context, to make it so it kind of shrinks it or compresses what's in the context. Um, It'll do this automatically if it gets to like 80% of the context window size. So Claude will take over and do that. Now the models, so again, going back to these things right here, the models in Claude are Haiku, that's the fast one, the very fastest. Sonnet, that's kind of the middle one. And Opus, that's the big reasoning engine. So this is for the tougher tasks, you put that on Opus. So you can change around which model you're talking. And this command here, slash stats, will let you know what your token consumption has been. Okay, so that's part of it. The tools, all right, there's some kind of built-in tools like the reading and the writing to the file system, and like the code sandboxes where we're actually running code. Those are kind of fundamentals. But then there's also MCP servers. Okay, so you can set up the MCP servers to call remote systems, or even local systems. You can set it up that way as well. Memory is mostly the file system, but a lot of people are using the Supabase, which is PostgreSQL. Um, and a lot of my own work actually is to try to get to get more of a nat. Well, there's a long story there, but I kind of think that it would be cooler to kind of get kind of a more um, to have a memory that's kind of more domain specific and that is like a nice kind of crafted schema for a particular application. So it has to do with like bringing things into the enterprise. But anyways, memory, right? Okay. And then we have this kind of notion of a conversation, which is something you start when you open a session with Claude. And there's these kind of important files like the Claude MD file, which basically loads into the context as the first thing in every conversation. So this is kind of like your master file that's going to kind of set the context. And then you can also load skills in there as well. And then files, of course, are always loaded into the context. And an important thing to remember here is that Claude, as it does stuff, is like reading a bunch of stuff and then it's writing its own kind of separate files that you can't see. And then it reads those back in and loads them into the context. So it's really using like the file system as kind of a working memory to kind of like, so it's not only long-term memory, but it's also this kind of working memory where it's kind of putting things in there and then later on it can then load those into the context. So it's very, that's kind of actually one of the big, that's actually there's a lot going on around that makes it so this is more and more effective. Okay, so some of the more advanced Claude Codes issues are we have the notion of subagents. So subagents, the thing about them is that you can spawn subagents, which are Claude Code agents, and they have their own context. So like you can spawn up a subagent to go and do the specialized task, and it's going to have its own context. It's not going to be mixed in with the I'm the kind of manager agent who's trying to kind of coordinate a whole bunch of subagents, and each of those subagents are given a more pure context that they get loaded, or they have skills as well that get loaded. So they're like focus specialists. So there's that whole that's there's that and they're doing a self-contained task. So the subagents is to really stand up kind of really big systems, you want to have subagents doing that. And then the normal way you do subagents is they only talk, it's a kind of like hub and spoke kind of system where they're only talking to the manager. But then you can also set up agent teams where the subagents can talk to one another or over a shared task list. So like you could have one that's like a front end developer, one that's a back end developer, another one that's a tester, and the tester then talks to like the different ones and runs tests, and they're kind of all doing their specialized tasks. Um, right. Okay. And then there's this whole issue of like you can have multiple conversations in the history. Um, some cool stuff now that's coming up is you can like paste in screenshots. Like you can like maybe you can have like a mock-up of what you want the thing to look like, the interface to look like, and Claude will get you part of the way there. There, of course, also is this whole issue of checkpointing, undoing, and rewriting around the and integration with Git. So this is really important because especially you want to be able to kind of like rewind stuff if you kind of like. So sometimes what will happen is you'll get yourself in trouble. Like it will, no matter, it's not perfect, and so sometimes you say, "Ooh, I don't want to do that." That's kind of like when I did my website using vibe coded, I vibe coded my website. And when I was doing that, I'd say, oh, that's not good. This is like kind of doing some weird artifact on the CSS. And I just don't feel like I don't want to go in there and try to figure that out. So I say, okay, back up, go back to the earlier step because that looks dangerous. I mean, I'm not sure how many vibe coded projects have entered into this kind of into this state where they're uncontrollable now, and there are bugs that can't be removed. Like they've reached a point where they can't back out of it. Um, well, they can always back out of it if they got it set up right with Git and everything like that. But what I mean is, I mean, they've gone down a path where they have these bugs that are kind of persistent bugs, and no matter what they prompt, like they'll fix that bug, they'll cause another one. And they're not getting kind of quiescence on the bugs. That's kind of an empirical question about when is that happening or how is that happening? Because that's a failure mode for vibe coding if you get to that point. And there's this thing, this Ralph loop. So there's this whole thing of it's interesting culture that goes around this thing, but there's this whole thing of like, well, it kind of gets a little bit monotonous to always be answering like questions from from Claude. Like it's like too much interaction. You just want to say, do it, okay? Just the answer to everything is yes. Just go, go, go. You can go into this Ralph loop where you put this minus P flag and it just runs roughshod. So people, I mean, it's really cool. I mean, like just the people are going, building these, and you can come back and you have this entire system built. You wouldn't have to kind of go along saying yes to things. All right. So what's going on though with the training of these coding models? So like Claude, like Opus, right? Or the Opus, for instance. Right. So does it relate to the training that we were talking about in the class? And the answer is absolutely. It's got a whole bunch of pre-training is basically the pre-training is what is like the thing that it's learning over. And those are like public repositories of code, documentation, Stack Overflow conversations, etc. So, when it does this, it's going to get kind of pick up some of the syntax of the different languages. Just going to pick it up in, just by doing the pre-training, by doing doing the compression. And then also it has supervised fine-tuning. So there is this corpuses or corpora of problem solution pairs that are going to get fed in, kind of give a little more instruction following. This chain of thought corpuses where we actually have, or we, I don't do this, but people that we, the field, whatever, do they have step by step, well, really kind of seriously annotated step by step instruct like paths that are followed to solve a problem. Okay, those are kind of really kind of very useful but expensive to obtain corpora. But you say expensive to contain. These people have money to spend to get corpuses. So one of the things you have to always remember, what's all this capital doing? A lot of it is they really kind of like generating like this the hardware. They got to like they have to kind of just do it, right? They have to kind of just siege the problem. So that it's a lot of labor that's going into that kind of preparing these things. And then, of course, reinforcement learning with verifiable reward. So there's a sandbox that actually will run the code. And of course, um, if the format's coming out right, that's good. We're gonna get some reward. And if you have the solution, the proper solution, give a lot of reward. So they're doing this whole kind of reinforcement learning kind of part of the problem. And then there's also a lot of synthetic data that's being generated to juice this training. So it's not like some of this is actual observed data in terms of like how you solve stuff. But then there's also a lot of synthetic data that's juicing the training. So this is how we get the model, right? Not the harness, the model. Um, or that's how I can say that. I'm not going to claim credit for what they're doing. Okay, so that's this is kind of how where it's all coming from. Okay, so now let's just talk. We're almost done here. Let's talk about the claw, the lobster. So I'm not sure what's really going on with this, but it was pretty fun when it first came out. I mean, I got into the spirit of raising the lobster claw. Uh, so basically, the idea behind this is this Peter Steinberger. He's kind of interesting character. Anyways, it's like the idea here is give the keys to the car to the lobster. So in other words, put everything on an Apple Mini. Okay, and he, OpenClaw has its own harness, right? But the thing what you do is you give it the account access. So basically, it's going to have its own email. You give it everything that you have, right? I mean, give it its own bank account, right? I mean, give it money, give it everything, and then you have to have a heartbeat. So you're just telling it, you're rousing it into like, so it's got to run, kind of like the agenda in Baby AGI, right? It's like there's always going to be something on the agenda, so it's always spinning, it's always doing. And then you just, the quote from Peter Steinberger is the lobster is loose, it's not going back into the tank. Okay, so there's all these teams that are just doing this, and everybody's just like, okay, so have I run OpenClaw? And the answer is no. And one of the reasons why is because I got a message from our support at the university saying, you're forbidden to run OpenClaw. They don't want this thing running around on our systems. I could run OpenClaw my own, like I could buy a bunch of stuff, but I'm not really that keen on doing that and run it on like now. But anyways, but it's cool to observe. It's cool to watch. But I have to say that I have not actually taken the plunge and run one of these agents just going hog wild like that. So where are we? Well, we're in the middle of a technological revolution with agents. I mean, so there's lots of specific harnesses. It's just like so much is going on there. We have we probably need a new UX kind of pattern because just babysitting Claude saying yes, 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 and all that stuff is wrong. One of the proposals is to make it more email-like, so you get a message after the thing spins for like an hour, and it tries to summarize and try to gives you kind of a best summary and kind of question about what should the next steps be. So this is kind of the human in the loop thing. And of course, this is like one of the ideas behind the human in the loop is that maybe when it first starts, it should be very like just like a real human assistant. It should be like kind of okay. Do you want me to do this? And then once it gets a sense that okay, actually I feel confident doing that, then it will you can delegate more to it. It's not coming back and interrupting you, or and it's not it doesn't need to be kind of handheld all the way everything through things. Yeah, the natural language, the whole thing of prompt going into LLM, it's spiky, because it's very sensitive to the inputs. So there's this whole context engineering effort of how do you actually piece together context engineering? How do you actually piece together what the prompt should actually be? Okay. Then there's also this thing coming maybe from LangChain stuff is like this traces of the whole thing. How can we bring the traces back in and kind of evaluate, do a little bit of meta reasoning over everything. And then finally, I just mentioned this to bring back this whole kind of like the old rational agent again. Maybe for enterprise applications, we do want to actually frame things as a single all-encompassing, and maybe a very complex performance measure, but a single overall encompassing performance measure. Because if you're given that, then you have the basis to do end-to-end training. So you have a harness, you have a model, and you have a objective function. So there's a chance then that you can then in this case, you'll be affecting the harness. The harness is what's going to the weight's on the harness somehow, or the behavior of the harness is what's going to be learned. But you're going to wind up being able to kind of like go through this end-to-end training to get harnesses that are kind of objectively better, for the performance measure. So it's like yet another kind of stage that's beyond um, there's another kind of level of training, another kind of level of scaling somehow that you can kind of be brought to bear. So I think the rational agent stuff might come back actually in that regard, because the enterprise is, the Enterprise is a little bit, the whole kind of like splendor of like this lobster running around doing all this crazy stuff. It's entertaining, but a lot of times the Enterprise, like serious enterprises, are a little bit like, ooh, reluctant. So you give them some kind of rational, bring back the rational agents and do end-to-end testing around that or training around that, then maybe. Okay, so I'll just end with the following question: is that okay? Well, this is all cool. This is all kind of like racing. I see like in the Matrix, I see those kind of like agents, and I see the robots in the Matrix, and I see all of science fiction. I see, wow, okay, so it looks like we have maybe the ingredients, but the question is the thing alive? Okay, is it alive? And then will it become artificial general intelligence or artificial superintelligence? Um, One thing to say is that it does feel a little bit more alive once we suspend the classical rational agent assumption. Okay. Because now it's bringing in LLM, it's kind of got this kind of, yeah, it's not just kind of following some objective function. And it may even get to the point, may even already be there, that it passes the Turing test. Okay. But we got to remember this, that passing the Turing test does not imply sentience. Okay. Um, and you get a lot of arguments with people about that, whether or not it does that. So just to keep out, to remember that there's this thing called the ELIZA effect. The person who's judging whether these things are truly intelligent is truly intelligent themselves. They're a human being who's making this kind of judgment. Now, so the question is that what are they bringing to that? I mean, one thing's the mechanical thing that's just kind of spitting things out, and the other one is a flesh and bones. We know it's, or we assume that it's a conscious sentient being. So maybe the conscious sentient being is reading into the things that's getting spit out. Um, this kind of it's ascribing sentience to it. And then just another point here is that it is actually when the thing is so sycophantic, which is really kind of you might actually even be more inclined to say that it's sentient because it's like complimenting you or making you feel good. Uh, but then, of course, these are all mysteries. We don't know. There's like a lot of philosophers that work with this, like the whole Chinese the room example, Searle. So if you want to look, Searle did a lot of but so the question of intentionality, self-awareness, and consciousness, and these are true mysteries. I think I'll say a little bit more about this. There's not much more I can say about it because it's just a mystery. It's like, I don't know. I'm not a philosopher. But it's very there's a lot of, yeah, actually maybe I can say a little bit about that more about that in the final lecture. But we'll leave it at this point now. So this is yeah, so that was kind of the snapshot I think of where I think agents are. And yeah, so all right. Okay, so we'll conclude there.